This is the hypothesis test part 3 video, type 1 and type 2 errors for MAT 120 section 1. So let's talk more about choosing a significance level. The significance level being the cutoff point for our choice of whether to keep or reject the null hypothesis. And recall our definition from earlier in the book, where we said the significance level is the point where the researcher thinks the evidence against the null hypothesis is convincing. In other words, that's the point where they think the probability of seeing those sample results if the null hypothesis is very small. So the unknown reality is that the null is either true or the null is false. And when we perform our hypothesis test with the sample data, we're either going to keep the null hypothesis or reject the null hypothesis. Now, if we keep the null hypothesis and the null hypothesis in our unknown reality is true, we are happy because we've made the right decision. Likewise, if we reject the null hypothesis, when the null hypothesis is false, we are happy because we've made the correct decision. But if we reject the null hypothesis, when it's actually true, we've made a type 1 error. Or if we keep the null hypothesis, when it's actually false, we've made a type 2 error. Back to our first example, where we were testing the modification of a drug to see if it lowered the side effects. And our null was that the percentage equaled 0.35 or 35%, and the alternative was that the new drug had reduced the side effects, so the percentage was less than 35%. So assume there are two possible actions. One is to stay on the old drug, and the other is to switch to the new drug. If you reject the null hypothesis in favor of the alternative, that means you think that evidence is pointing to the fact that the proportion with side effects has been reduced. So you would want to switch to the new drug. On the other hand, if you kept the null hypothesis, you would want to stay with the old drug. You have no evidence that the new drug is any better. Now, if we reject the null hypothesis when it's actually false, we've made a correct decision, and switching to the new drugs was the right thing to do. If we kept the null hypothesis, when it's true, we're going to stay with the old drug, and if the null hypothesis is true, we've made the correct decision. Now, what about if we reject the null or throw it out in favor of the alternative? That's when we've made one of those type 1 errors. So let's break that down. Our action when we reject the null was to switch to the new drug. If we're making a mistake when we do that, the mistake is to when it does not reduce side effects. Our action when we keep the null hypothesis is to stay with the old drug. And if we're keeping the null hypothesis when it's false, we're making a type 2 error when the new drug does reduce side effects. Generally speaking, type 1 error is to conclude you have a difference when there's not a true difference. Type 2 error is to conclude you do not have evidence of a difference when there is a true difference. Often type 1 error is to take an action when you shouldn't, and type 2 error is not to take an action when you should. I say often because there are some exceptions to this rule. An example would be like quality control testing. So the second example we looked at was this one about the late start time. So a school board decides that if more than 60% of high school drivers in the district report that they often drive while drowsy, they are going to move the high school start time from 7:30 to 8 o'clock. And I see here that I should have added the hypothesis in here just to remind us what they were. So I've written that up here. The null was P equals 0.6, coming from right here. And the alternative was P greater than 0.6, coming from the fact that they are going to make their decision based on if they see evidence that more than 60% of the drivers are driving drowsy. So let's assume the two possible actions are to change the start time to 8 o'clock or to keep the start time at 7:30. If we reject the null hypothesis, so if we reject this idea in favor of the alternative, that the evidence points to more than 60% driving drowsy, which action will we choose? Well, in that case, we would change the start time to 8 o'clock. Now, on the other hand, if we kept the null hypothesis, meaning that we did not find any evidence in favor of the alternative, our action would be to keep the original 7:30 start time. So let's break down the two types of error, type 1 error and type 2 error. So type 2 first. Okay. Our action when we reject the null hypothesis, and if we're rejecting the null hypothesis, when it's actually true, we are making an error, a type 1 error, when the null is true, or when the percentage driving drowsy is 60% or obviously less. So putting that all together, we have our type 1 error is to change the start time to 8 a.m. when the percentage driving drowsy is 60% or less. The null is true. And our type 2 error, on the other hand, is to keep the null when it's false. Our action when we keep the null is to keep the 7:30 start time when the percentage driving drowsy is more than 60%. Now, which one of these mistakes is worse? Okay, well, I would think that keeping the 7:30 start time when students are driving drowsy would be a safety concern and also possibly affecting their learning. So I would lean in the direction of saying this type 2 error is worse in this case. Now let's go back to our first example for a second. On this one, which mistake is worse? Switching to the new drug when it does not reduce side effects, or staying with the old drug when the new drug does reduce side effects? So there's a lot of questions related to this that you would want to know, like what other side effects might the new drug have? Does the new drug work as well in the actual treatment of the problem being treated? What's the cost of the new drug? So a lot of these things would have to be factored into determining which one of these mistakes was worse, the type 1 error or the type 2 error. Calculate it. So let's go back and talk about this little chart that we started with again. Now, type 1 error, as we said, is the significance level. And that's chosen by the researcher. And for example, 5% is a commonly used significance level. So why would anyone want to choose a significance level of 5% when that means that they're saying, okay, I'm okay with making a type 1 error 5% of the time? Why wouldn't we just choose type 1 to be 1% or even a 0.5%? And the reason is, as we'll see more on the next page, is there is a trade-off between type 1 error and type 2 error. As type 1 error goes down, type 2 error increases. And likewise, as type 1 error increases, type 2 error decreases. So we can't just choose type 1 to be arbitrarily small, because if we do, that's going to make our type 2 error very large. So the choice of a significance level should depend on the consequence of making a type 1 error versus making a type 2 error. If a type 1 error is worse, a researcher should consider choosing a small significance level, like 1%. If a type 2 error is worse, a researcher should consider choosing a large significance level, like 10%. But the reality is that usually 5% is chosen, and not a whole lot of thought actually goes into the choice of that significance level. And in the last couple of years, there's been a lot of criticism leveled at the idea of just choosing 5% all the time without giving it a lot of thought or really understanding what p-values are measuring. So, if the null hypothesis is true, what percentage of the time will the p-value be less than 5%? So let's recall our definition of a p-value. The p-value is the probability of seeing the sample data, or more extreme, just by chance if the null hypothesis is true. Okay? P-value, probability of seeing sample data just by chance if null hypothesis is true. So 5% of the time, the p-values will be less than 5% if the null is true. So our cutoff point between keeping the null hypothesis and rejecting it is our significance level. For example, 5%. And anytime there's an area of 0.05 or a p-value of 0.05 or smaller, we are going to reject the null hypothesis. But if this is the true null distribution, and we see a p-value in this area, we're going to reject the null, and that will be an error. So this is our type 1 error. On the other hand, if we're on this side of the cutoff, we're going to keep the null hypothesis. Is a picture of the null distribution. Now these graphs on the bottom are aligned with the graphs on the top, And this shows a picture of the case where the null distribution is not the true distribution, but instead the true distribution is some alternative distribution. But we're going to have the same cutoff. So on this side we're going to reject H null, and on this lower side of the cutoff we're going to keep H null. But if we keep the null when this is the true distribution, that means everything below that cutoff, all this area in here, we're going to be making an error. And this area here, on this alternative distribution, is the type 2 error. Information. So recall, we know what the type 1 error is because the type 1 error equals the significance level, and that's chosen by the researcher. So if the test is being done at the 5% significance level, the type 1 error equals 5%. But what about the type 2 error? So from our last example, our null hypothesis was p equals 0.6. So this is one single value, and it's one single distribution. But the alternative was p greater than 0.6. There's a lot of values of p that are greater than 0.6. So that includes p equals 0.61, p equals 0.62, p equals 0.63, and so on and so forth. And it equals all those values and the values in between as well. So what's pictured here in this graph that we looked at on the previous page is just one of many alternative distributions. So you can think of it as looking more like this. And each one of these distributions has a different type 2 error. Close to the null hypothesis is going to have a large type 2 error. And the distribution over here, far away from the null hypothesis, is going to have a small type 2 error. So to calculate the type 2 error, as we said, you need a specific alternative in mind. And the type 2 error is actually a function, so like a graph with p on the x-axis, all the different possible alternatives, and type 2 error on the y-axis. So this is a complex thing to calculate, and we will not be calculating type 2 error in this class. But you should know what you know and what you don't know. So there are questions on the homework, and there will be questions on the final that say, what is the type 2 error? And the answer is, you need more. So people tend to talk more about the power of a test than the type 2 error. You'll hear people ask the question, is it a powerful test? So power is very simply 1 minus the type 2 error. So if you know the type 2 error, you can get power, and vice versa. Power is not giving us additional information beyond what we would have with the type 2 error. And when people say a test is power, that's another way of saying that the test has a small type 2 error. So on this picture here, if this area right here is the type 2 error, then this area here is the power, which is also shown on this same thing on that graph, on the second graph. So there are two ways to reduce the type 2 error. Okay, one way is to increase the significance level, which is the type 1 error. So recall from the previous slide, there is a trade-off. As type 1 error increases, type 2 decreases. So one way to reduce the type 2 is to increase the type 1, which is the significance level and is chosen by the researcher. The second way is to increase the sample size, because as the sample size increases, the estimates become more accurate and the probability of making a mistake decreases because you've got more accurate results. But if the type 1 error, the significance level, stays fixed, any benefit that you're getting in the reduction of error by increasing the sample size all gets poured in to the type 2 error. So increasing the sample size decreases the type 2 error. And although it's beyond the scope of this class, planning can be done in advance such that the sample size can be calculated based on a desired power at a specific alternative hypothesis that the researcher thinks that is an important difference. If that's the difference that exists, I want to be able to detect that difference. Now, one last detail I want to mention about hypothesis tests is, can p-values ever be greater than 0.5? And this is only going to happen if the data goes in the opposite direction of the alternative hypothesis. And that rarely happens because generally the researchers have some idea of which way the results are going to go, but it can happen. And what I mean by the data going in the opposite direction of the alternative hypothesis is, so for example, on the example that we just, the second example, we tested p equals 0.6 versus p greater than 0.6. So what if p hat equaled 0.59? We're never going to find evidence that the true proportion is greater than 0.6 when we actually witnessed a sample proportion that was less than 0.6. In this case, if you did all the calculations, the p-value would come out to be something greater than 0.5. But you would never actually get to the stage of calculating that p-value if you recognize that with a p-hat of 0.59, you're never going to show that it's actually greater than 0.6. So at that point, you could just stop. And likewise, going back to our very first example where we tested p equals 0.35 versus p less than 0.35, what if p hat was 0.36? Well, again, we're never going to show it's less than 0.35 if our sample percentage is 0.36. So at this point, you would just stop. And so while p-values can be greater than 50%, we really don't ever get to that point of calculating them, because we just stop before we get there, because we know what the outcome of the hypothesis test is going to be. So on page 162 are the same steps that were spread out across several pages earlier, just summarized all on the same page. And I did notice that my ordering somehow got out of whack here, or the numbering, so that was not on purpose. So those numbers should align with what was on the previous pages. So our 6 steps are: state the null and alternative hypothesis. Second step is the researcher specifies the significance level, at which point in real life the data would be gathered. And then with the data, calculate a test statistic, use the test statistic to find the p-value. Once you found the p-value, compare that p-value to the significance level, and then after making that comparison, make a decision about the null hypothesis and a conclusion about the alternative hypothesis. So this is just everything on one page, so to make it easier for you to refer to. So at this point, you should pause the video and do in-class exercise number 20B on page 61. After you've done that, then you can start up the video to check your work. So in this problem, it says, in the first problem, which is for some reason labeled number 3, it says, if the percentage of adults in Maine who have visited a dental clinic in the last year is lower than the national percentage, they will launch a public service campaign. So if they reject the null hypothesis in favor of the alternative, then the action that they're going to take is to launch the campaign. And if they were to make an error, the error would be to launch the campaign when it is not needed. On the other hand, if they keep the null hypothesis, they're not going to launch the campaign. And the potential type 2 error would be do not launch the campaign when it is needed. So on the second problem, if they reject the null hypothesis in favor of the alternative, that's going to say that a majority of students rated this as important. So the action would be to encourage group work, and the type 1 error would be to encourage the group work when it does not contribute to academic success. So even when I do this, I'll jot down off to the side, type 1 error is to reject null when true. And I ask myself, what's the action if I reject the null? And then what's the mistake that's made if the null is actually true? And then the type 2 error is the opposite error. So once you have the type 1 error, the type 2 error is easier. So if type 1 is encourage group work when it does not contribute to academic success, then type 2 is to not encourage the group work when it does, or to not encourage group work when it does contribute to academic success. So at this point, you should do the hypothesis test for proportions part 2 WebAssign, which is due April 26th. And that is it for tonight.